Welcome to a lesson with Dr. Powell. Let's take a look at how we can investigate convergence or divergence of this series by taking the terms and comparing them to the terms of a geometric series, kind of in a ratio type way. All right, so this is one term. Let's call this a sub n. Let's just kind of think about what's going to be happening. As we go to the next term, a sub n plus 1, we multiply by something. So I'll call this Rn. Then to go to the next term, we multiply by something else. Notice how it changed, but it's going to change. I mean, what are we multiplying by? Quite literally, we're multiplying by the ratio a sub n plus 1 over an. If we multiply an by this, we get this. So we always kind of have something to multiply by to move from here to here. But the issue is this is not a geometric series, so these r's values are going to be changing, and so forth. So we have this, so we kind of have this sequence of Rn's, right? So we kind of make a new sequence. The sequence is Rn. And the question is, do the Rn's actually converge to something? Like eventually, are the Rn's actually getting close to the same thing? So pretty much, is this series or this sequence, just the sequence of terms right here, is the sequence of terms eventually behaving like a geometric sequence? Like eventually, like the values of r are going to be very close to each other, not exactly the same, but very, very close. So you're almost like multiplying by a value of r each time. I mean, by the same thing each time. Now, what happens if that is true and it is limiting? Then, and it limits to L, that means that eventually, for big enough n, you're going to be really close to L. R is going to be very close to L. So if n is big enough, then there's even like an epsilon tolerance around L, that it'll always be in. So these Rn's themselves will always be in within this. So let's suppose that R could be, so it's going to be bouncing around between L plus epsilon and L minus epsilon. Now, since this limits, we can make this epsilon as small as we like. It just will push this n further in the sequence to make it work. But really, we can really squeeze that in. So, well, what does that mean? That means that the sequence itself is behaving less than, in absolute value, a sequence that's, and let's just think about absolute values here. Here, let's just consider the absolute values of these terms and the absolute values of these ratios even. Okay, let's just do absolute values. So you can kind of think of all this in a positive sense here. Then at biggest, the sequence is behaving like something with an R value, a geometric sequence with an R value of this, and at smallest with an R value of that. Now, what happens if this limit is less than 1? If the limit is less than 1, then actually you can push epsilon small enough so that this top line is actually below 1 itself. So if L is below 1, you can move this top epsilon small enough so that you're actually less than 1 as well. So you can know that this geometric series is behaving less than a geometric series with L plus epsilon and bigger than 1 over here. But that's kind of nice. So that would mean that you definitely converged. So really, if this limits to something that's less than 1, so if it has a limit and that limit is less than 1, then we've actually bounded our sequence, like the terms of our sequence, bounded up, like each term is like smaller than a term of a geometric series that converges. So we would get convergence. So all we have to do is take a limit of this ratio and see if it's less than 1. If it's less than 1, then we've compared it to a geometric appropriately for convergence. Now, what happens if this ratio is greater than 1? Then you kind of reverse this picture. If it's greater than 1, then 1 is down, then you can fit this line above 1. And so you know that we're actually bounded below by a geometric series that we know diverges. because the R value is bigger than 1. So we'll know we have divergence. That's so if the ratio now is so if L is greater than 1, so in this case we have convergence right here, convergence. In this case down here we'd have divergence. So it looks pretty much just like a geometric series test almost, right? Where we're kind of like limiting to an R value. Instead of having an R value, we limit to 1, and we see if it's less than 1 or bigger than 1. The only thing that we don't really know, though, and this is just for absolute convergence, right? But the one thing that we don't know is we don't know what happens as we go to 1. Okay, we don't know what happens when the limit actually is equal to 1 in this case. So what does that look like? Well, yeah, I mean, what if the L value was right at 1? So we're using this bounding technique. So we know that the geometric series is less it's less than 1 that diverges and it's greater than 1 that converges, but you don't really know. So the test is inconclusive. So this ratio test for absolute convergence only works when only works when the limit is bigger than 1 or less than 1. And if it's the limit's equal to 1, the test is inconclusive. Let's now take a look at this particular series and see if we can determine if it is absolutely convergent or divergent. Now, already looking at this, we know that these terms are all positive because there's no negatives in here and whatever else. So really, this is absolute convergence. In this case, is just regular convergence. Now, however, what would happen if we had like a -1 to the n power? Then for this test, we would just ignore it. We would just ignore that so that we could focus on the absolute convergence part of it. Okay, so we kind of ignore negatives or just make everything positive in order to apply this test. So really, we just kind of look at this to apply it, and we're going to be looking at the ratio of an plus 1 over an. So we could think of this in a couple ways if we want. We could think of this as an plus 1 times 1 over an, which is literally just like taking the reciprocal of that. So let's kind of write that out. That's like n factorial 5 to the n squared, n plus 1 factorial. We just took the reciprocal. This is like writing this exactly the way it is, but we just replace n everywhere with n plus 1. So we have n plus 1 quantity squared, and then in here, this is n plus 1 plus 1, so that's just an n plus 2 factorial all over, and then here, this would be n plus 1 factorial and 5 to the n plus 1. Now, maybe we should have simplified this before we did this, because this actually does simplify a little bit. But in general, this is kind of the idea. So this part is just the reciprocal of what we see here. And this part is just the same as what we see here, but we just replace all your n's with n plus 1s. We multiply this out, simplify, cancel a lot of things, and then take a limit and see if what that limit is. If it's less than 1, we get convergence. Greater than 1, divergence. Equal to 1, we don't know, and we have to default to another test if we can. Okay, so we could go ahead and simplify this, but let me give you the alternate way if we first simplify these terms. Notice this is n plus 1 factorial over n factorial. What does factorial even mean? It means this. It means taking your number that you start with. So that's what this exclamation point means. It means factorial. So we have n plus 1, then you do the next one down, which is n, and then the next one down is n minus 1, and you keep doing this until you get to 1. For instance, what's 5 factorial? 5 times 4 times 3 times 2 times 1. You just start at the number and you just multiply integers one less until you get down to 1. That's what factorial means. So if you know that, so if that's what n plus 1 factorial is, right? So it's n plus 1, then 1 less than it, n plus 1, then 1 less than that, and so forth down. Then what's n factorial? N factorial is n times n minus 1 times it all the way to 1. Notice that we get a nice cancellation. So really, in the originally, we don't even have factorials. We simplify, so we don't even have to do this. All right, I just want to point that out because sometimes you can get lost over here if you're not comfortable with them. But you can also kind of get a sense. You could also do the cancellation right here and kind of work it out. Like here, you could do the same cancellation, which we just did. And then here, notice that n plus 1 factorial times n plus 2 is actually n plus 2 factorial. So we could actually get rid of that. And we just have this. And that would be the ratio. Now we would get this. This would be exactly what we got if we would have just started out with that. And we can just remind ourselves of that. So quite literally, so what do we do? 1 over an is just the reciprocal of this. Hey, it's right there. And then this is the same thing as this with an n plus 1 plugged in. So we have an n plus 1 plugged in here, n plus 1 squared, n plus 1, n plus 2. That's great. 5n. Okay, so however we do it, we get our ratio. Okay, our simplified ratio. Now we can kind of work with that a little bit more. Let's try to take we want to take the limit of that as n goes to infinity. All right, we can simplify a little bit more. See this 5 to the n and this 5 to the n plus 1. So this is like 5 times 5 to the n, right? So that cancels with that. So we just have a 5 in the denominator multiplied by this polynomial. And then we have this polynomial on the top. Notice that the degree of this polynomial is degree 3. This is degree 3. The leading coefficient, so leading term is n cubed even. So leading coefficient of that is 1. So n cubed up here, n cubed down here. And when you're taking a limit of polynomials and they have the same degree, then the limit is just the ratio of the coefficients. You could see that by a repeated application of L'Hopital's rule, because eventually all of the smaller degree terms will vanish in repeated applications of L'Hopital's rule before the leading terms will. And so really the limit just depends on leading terms only. So you really can just pretend like the other ones don't exist even, and that's fine. And then that ratio, you just get the ratio of coefficients. So the coefficients are just 1. So really this part right here, as we take a limit as n goes to infinity, the limit of this part is just 1, of this polynomial part. And that often is the case when you see a polynomial in here, or fraction or whatever, it often, because in this ratio process, kind of gives us a limit to 1 often, even if we have different like constants in here multiplied, because those same constants will appear down here as up here. So this part didn't really affect anything in the ratio, but the thing that was affected was that did happen is we were left with like we basically just have a fifth after we noticed this part limits to 1, then we just have a fifth left over because this was a 1 over 5. So this whole thing limits to a fifth. Hey, a fifth is less than 1. What does that mean? So our limit is less than 1, which means that our original series actually converges, and it converges absolutely. So this was just a test to see if it converges or didn't, and we found that it did. Thanks for watching.